I'm going to draw for you a box diagram of our heart. Kind of a quick schematic, and this is, let's say, divided in half, and I'll divide it in half again because we know the heart has 4 chambers, right? And the blood enters in the right atrium, goes down into the right ventricle, and then it goes over to the lungs, comes back out to the left atrium and left ventricle, and then out to the body. So that's kind of the flow of blood. And we know that the heart is a pump and it squeezes in a very nice coordinated way. And where that signal for squeezing begins is right here. So in the right atrium, if you were to zoom in and look very carefully, you would see a little clump of cells. And those cells, we call them the SA node. That SA node is just a clump of cells. And that sends off a signal very quickly after it starts the depolarization wave. It heads off a signal to the left atrium through what we call Bachmann's bundle. That's just a name for that little band of tissue. So Bachmann's bundle is that little band of tissue that heads over the left atrium. And then there are a few other bands that actually head down this way to this node of tissue, so a second node of cells. And these paths are called the meaning between, intranodal tracks. So you have these 3 intranodal tracks taking the message or the depolarization wave over to the atrioventricular node. So we've got a basic scheme or picture of now how the electrical signal gets sent through the heart. And if these are the highways, just remember that there's also signal that's sent through the actual muscle, right? So this is all in the wall of the muscle. And so if you were to actually kind of zoom in, you would actually see that these tracks are buried inside of muscle cells. So there's cardiac muscle cells all around here. And these muscle cells also get the signal, right? So they have signal going through this way. Actually, let me show with the yellow arrow. Signal going through this way and through the electrical conduction tissue. But there's also signal going this way, right? There's also signal going into the muscle itself. And it's actually leaving the SA node to go into the muscle, etc. So you see how there's actually signal that's going into the muscle, but there's also signal going through those blue or those light blue lines that represent the electrical conduction tissue. And the key here, the key issue is that the signal, the depolarization wave going through the electrical conduction tissue is much faster. And that makes sense because if it was going pretty slow, or if it was going the same speed as the muscle, then why would you even need it? You wouldn't need it. You could just have muscle. It's the fact that the signal can be sent much quicker, and that's why I was using the analogy of the highway, through those blue bands is why we have them. We want the signal to get quickly to the left side, so the left and right atrium contract together. And we also want the signal to quickly get over to the AV node. So that's kind of an overall view, but let's now zoom in. And actually I drew this out earlier, and you can see now exactly what this could represent. So in blue now we've got here, this is the SA node, and this is our, let's say, Bachmann's bundle. So this is kind of the cells that are going to take our signal to the other atria, Bachmann's bundle. And then you've also got these 3 intranodal tracks, right? Intranodal tracks that are going to take the message down to the AV node. So this is kind of a rough diagram. And on the outside, you've got all the cardiac muscle, all the muscle cells are there. So the 2 things you should notice right away, one is that if you actually look here, these are gap junctions. And you can see that I've drawn gap junctions all over this diagram. So you can see little holes and connections between cells. And all that means is that ions that are in one cell will actually start leaking into the next cell. So if you've got a few positive ions in one cell, they'll leak into the next cell and make it slightly less negative. And that's actually really important for depolarization. Now, the way I'm going to show depolarization is that all these cells, they have a little negative sign in them, right? So these negative signs represent the membrane potential. So for example, we know that the negative sign in this muscle cell probably represents somewhere around negative 90 millivolts, because that's usually where these cells like to be. And inside, these are usually somewhere around negative 60 millivolts. But in both cases, they're negative. And if they go positive, we call that depolarization. I'll actually shade in the cell, and that's how you'll know that that cell in particular has depolarized. Now, the fact that all these cells are interconnected through little gap junctions, it means that these cells are a functional syncytium. And I'll actually write that out here. Functional syncytium. And syncytium is kind of a funny word to spell, and that's how it's spelled. So functional syncytium, all that means is that these cells are basically, they're mechanically, they're chemically, they're electrically connected to one another. So really, in a way, it kind of starts to resemble an enormous muscle cell. They're not actually one cell because they all have their own nucleus, and they're actually, in other ways, behaving like individual cells. But the fact that they've got all these little connections between them allows them to act in some ways like one giant unit. And that's why when you look at the heart, it beats kind of all as one. And it's because it's so well coordinated. So let's focus in now on the depolarization wave. So this is kind of the whole point of this, is to show you that I'm going to make a little space now. The depolarization wave, how it happens. So let me actually write that at the top. Depolarization wave. And you're going to actually see how it goes through. Depolarization wave. So let's say that, wave. So now let's say that one of our SA node cells decides to depolarize. And we know that they can automatically depolarize if they want to. So let's say that this cell over here depolarizes. So this is our first cell depolarizing, and I'm going to shade in the cells as they depolarize. We know that that means that they go from negative to positive. So if that cell depolarizes, what's next going to happen? So these little positive ions, specifically calcium, are going to leak into these neighboring cells, right, through the gap junctions. And those cells, if they were already negative 60, they're going to start rising, right? Their membrane potentials will start trickling up as the positive ions go in there. And at some point, they're going to hit their threshold for firing. And so they're going to fire off and become depolarized. And when I say fire, I basically mean become depolarized. So they're going to become depolarized themselves because they hit their threshold for doing so. And so they become depolarized. And then they have some positive ions. Again, depolarization means you have lots of positive ions floating around inside of you. They're going to have some positive ions that kind of float into their neighboring cells. And so now more cells are going to kind of feel the effects of the fact that there is this depolarization wave that's beginning. And so now these cells are going to fire. And the SA node cells are fantastic at conducting this wave. So the depolarization wave, this is all about conduction from their own cell into a neighboring cell. And they're really, really quick about it. So now more cells are getting depolarized. Now, I'm going to pause quickly, and I'll show you what happens in just a few moments. So soon you might get something like this, where now you've got more of the SA node cells have depolarized. You've also got a couple of the myocytes have depolarized as well. And so I've shown you 4 of the myocytes that have depolarized now. And so you can see again that the signal definitely does get into the myocytes. But what happens after that is that the myocytes, they actually don't propagate the wave as quickly as the electrical conduction cells do. And so you'll see that difference when I speed this up one more time. You'll see how the signal definitely keeps moving through the electrical conduction system, but the myocytes aren't as fast, and so it doesn't move as quickly. So let me speed it up for you one more time. So now it moves even further along, and so you can see now the signal is going along the electrical conduction route, but still you haven't seen the myocytes themselves propagate the wave. And so as I speed this up one final time, you'll see exactly how that might happen. So this is what it would look like if we let it keep going. And so you can see finally for the first time we have some cells down here. I'm going to circle in white, and maybe even one up here, that's actually getting a signal from a neighboring myocyte. So definitely depolarization waves go through myocytes. There's no doubt about it, of course. But what I wanted to show you is that you can actually move much further along using just this electrical conduction signal this way and going this way and down the internodal tracts in all the directions than you would if you were just using and relying on the muscle cells, because they don't conduct as quickly. So the depolarization wave is going in all directions, but some directions are moving more quickly than others. And also just keep in mind that when I say that ions are traveling between cells, when it comes to the electrical conduction tissue, most of those cells are going to be sending calcium ions to their neighbors. But once you get into these cells, these myocytes, now you've got actually, for example, actually let me draw it in maybe a different color. Now you've got actually some calcium, but also some sodium that's leaking in. So here you've got some sodium leaking into these cells too. So both calcium and sodium are going to be leaking between the myocytes, whereas between the electrical conduction tissue, it's mostly calcium that's leaking between cells. So positive ions are slightly different in the two cases. So this is a depolarization wave, and I think now you can kind of see how it looks in a slow motion, sorry, I flipped it, in a sped up view.